These are our 1-5 notes on inverse functions. We're going to look at the definition of an inverse function and then how to find inverses numerically, graphically, and algebraically. Let's start with this example. The rate, that's one of our variables, at which crickets chirp is a function of the temperature of the air around them. So I could write in math, rate is a function of temperature. That identifies temperature as my input, my x, and rate as my output, my y. So in this table, I have some data, and it gives me values for the temperature, right? That's my input, and corresponding values for the chirps per minute, the rate, which is my output. So what if we know that crickets were chirping at a rate of 55 chirps per minute? Well, we find that value in the output column of our table. Could we determine the temperature? Well, sure. If we go 55 chirps per minute, that is paired with 60 degrees Fahrenheit. So to do this, we used the output, right, which was chirps per minute, as the input, and we used the input, which was degrees Fahrenheit, as the output. So just as we can find y of x, so y using x, we can define x of y, so x using y. And you'll notice here that where we put our variables x and y has switched places. Now, let's look at some symbolization for inverse functions. Oh, nope, going back. Important information here. So let's go back and look at our definition. The inverse of a relation, remember a relation is any set of points, is formed by interchanging the two variables, so just switching their places. So if we were to find an inverse numerically, we're going to interchange the input and the output. We're going to switch where x and y are in our relation. So if we take our set of points, our y's were chirps per minute, right? That was our rate. And what we had in that y column, which was our output column, was 0, 0, 5, 30, 55, 80, and 105. Those were chirps per minute. And what goes now in our output column, right? So this is our input column. This is now our output column. Are our temperatures, which were 20, 30, 40, 50, 60, 70, and 80. So I have a new set of points, right? This is a relation. It's an inverse relation because we switched the input and output from our previous information. And the question is this a function? And the answer is no. And the reason the answer is no is because we can see in these two sets of points, right, that for the same x is repeated here, these are the same, we have two different y's, two different outputs, right? These are different. So based on the definition of a function, we could say no, because for the same input, right, in this case 0 chirps per minute, there are two different outputs. So there was not one and only one output here, and that would be 20 degrees Fahrenheit and 30 degrees Fahrenheit. Okay, now we're ready for our next page. We're we're going to look at the symbolization for inverse functions. Right? So if we have a function, we can use f of x to designate that function. And its inverse is also a function. So the inverse is also a function. We can designate that with this notation, where we read this as f inverse of x. So the f is here, the of x comes from those parentheses, and the superscript of -1 is read as inverse. Now be careful. We are familiar with putting a superscript of -1 on a number and it meaning reciprocal. So if I had 3 to the -1, it would mean the same thing as 1 over 3. But when we put the superscript of -1 not on a number but a function name, it doesn't mean, right? It does not mean the reciprocal of f of x. It means the inverse. All right, now we're ready to look at finding inverses graphically, which is based on the same idea as finding inverses numerically. So when we have a graph of a function, we're going to start by identifying points. That makes it numerical. We're going to interchange the x and y coordinates, which will give us points on the inverse. And then we're going to plot those points from the inverse, and we're going to connect them in order, right, with a smooth curve. So let's take this. This is the graph of the points we had in our No, it's not. So this is the graph of a function, right? So this is my f of x. And we know its function. It would pass the vertical line test. And I have several points marked on this, and I'm going to label them from left to right. So I'm going to call this point A, this is point B, C, this is point D, and this is point E. And I'm going to take all those points and I'm going to switch the x and y. I'm going to interchange them. So instead of having -3, -1, I'm going to go to the point -1, -3. And I'm going to label that, right? So that's -1, -3. And I'm going to label that with a little a. Come in here and erase that. Okay, let's go on. So -2, 1 becomes the point 1, -2. Okay, and I'm going to label that little b. Right? That is the point 1, -2. 0, 2 becomes the point 2, 0. And I'm going to label that C. That's 2, 0. And then 2, 2 doesn't change. Switch 2 and 2, we still have 2, 2. So that is little d. And then 5, 6 becomes the point 6, 5. So that's 6, 5, and we're going to label that little e. So those are points on my inverse, and we're going to connect those with a smooth curve going in ABCD order. So I'm going to come in here, and I'm going to come, oh shoot, to reach this point, we're going to have to curve out to here. So we'll take that off. All right, so that forms an interesting pair, doesn't it? Okay, here are the features of the graph of functions and their inverses. One is that functions and inverses will always graph as reflections across the line y equals x. So I'm going to come in here and I'm going to graph the line y equals x. So that line is going to go right like that. And you can see that my blue and green graphs are mirror images across that line. And that was the line. Y equals x. Right. What's also true is that horizontal features, right, like asymptotes or x-intercepts, will become vertical features, and vertical features will become horizontal features. So one thing you can notice is that the graph of f had a y-intercept at 2, whereas the graph of the inverse has an x-intercept at 2. All right, now the meat, finding inverses algebraically. So here we're going to take as our example, right, the function, I'll call it f of x equals 2x plus 3, and you'll remember that is a linear function. Okay, the first thing we're going to do when we find an inverse algebraically is we're going to write the function as y in terms of x. So we're going to take this f of x and we're going to replace it with y. So I have y equals 2x plus 3. This is our function. Okay. Now, very easy to get an equation of the inverse of that function. We're going to interchange x and y. So where we see y, we're going to replace it with an x. And where we see x, we're going to replace it with a y. And we would do that, right? Every x would be replaced with a y. Every y replaced with x. Okay? So this is an equation of the inverse. But we would like this equation solved for y. So we're going to solve this equation for y. So if I have x equals 2y plus 3, and I want to solve it for y, then I'm going to have to subtract 3 from both sides, and I end up with x minus 3 equals 2y, and then I'm going to divide both sides by 2, and I get, I'm going to put y on the left side, y equals, distributing that division of 2, I get x over 2 minus 3 halves. Right? That could be rewritten as y equals, right, dividing by 2 is the same thing as multiplying by 1/2, so y equals 1/2 x minus 3 halves. Well, hey, that's a linear function. Okay, and which means it is a function. So when you solve for y, when you're finding an inverse, and you solve for y, if it's a function, then we can write that inverse in function notation. So the y now gets replaced with f inverse of x because the inverse was a function, and we get the inverse of f is 1/2 x minus 3 halves. And now, right, compositions of inverse functions. Because what a function does, the inverse undoes, then if we put, right, if we compose f with its inverse, so put the inverse function inside of f or go the other direction, the output should always be x. Let's look at this example. I have f of x is equal to 2x plus 3, and I have the inverse of f is 1/2 x minus 3 halves. So I'm going to come in here and I'm going to find f of the inverse of f, right, and see if we end up with x. So I want to find f of the inverse of f of x. We start with the inner function, which is, right, 1/2 x minus 3, so that would be f of 1/2 x minus 3 halves. And now we're going to take what's inside the parentheses following f and put it where x is in f. So that would be 2 times my input, which is 1/2 x minus 3 halves. And then we have our plus 3. Okay. To simplify that, we're going to take this 2 and distribute it across the subtraction sign, and that gives me 2 times 1/2 is 1, so just x, minus 2 times 3 halves would divide out the 2's, so we would get minus 3, and then we have our plus 3. Those subtract out, leaving me just x, exactly what I was looking for. Let's go the other direction. So this time, right, let's do the inverse of f of x. So that would be the inverse of what f of x is, which is 2x plus 3, And this tells us we're going to use 2x plus 3 as the input for the inverse function. So that gives us 1/2 of 2x plus 3 minus 3/2. Distributing this 1/2 across this addition sign gives us, right, 1/2 times 2 is 1, so x plus 1/2 times 3 is 3/2 minus 3/2. Those 3/2 subtract out, and again, we get x, exactly what we were looking for. And when we do this, we are showing, right, that they're inverses. All right, which functions have inverses? We already know that a function is a set of points where there is only one y for every x. We already know that the graph of a function will pass the vertical line test. What's new to know is this: a function which has an inverse. So I've got a function, it does these things. If its inverse is a function, right? So a function which has an inverse, right, that is a function. We'll have only one y for each x. That makes it a function, but also we'll have only one x for each y. When this happens, our function is called 1-to-1. 1y to 1x. 1x to 1y. The equation of an inverse function will have only one expression for y. So an equation would have to say that y equals one thing, not that it could equal two different things. Let's take this as an example. I have f of x equals 0.5x squared plus 2. That is a quadratic function. Okay. Notice that x is squared, right? Outside that, we're multiplying by 1/2, so that's a vertical dilation by a factor of 1/2, so it's going to squish it down vertically. And we are adding 2, so that's a vertical translation up 2. Question, is this a function? Well, look at our x's. Every x is different, right? So there is never the same x paired with two different y's, right? So the answer would be yes. There is only one y for each x. Is it 1-to-1? Well, the answer to that question is no. You'll notice that y's are repeated, right? And then they are paired with different x's. So why is it not 1-to-1, right? Because there is more than one x for the same y. So, is its inverse a relation or a function? And the answer would be it is a relation because it is not 1-to-1. All right, now a function that is 1-to-1 will pass a vertical line test because it's a function, but it will also pass a horizontal line test. So if we plot the graph of 0.5x squared plus 2, right, we already had some points for this, so we know we're going to have y-axis and an x-axis. And we had the point, let's make that on a scale of 1, so that's 1, 2, -1, -2, and 1, 2, 3, 4 on a scale of 1. So we had the points -2, 4, right? That was here. We had the point -1, 2.5. That was here. We had the point 0, 2, 1, 2.5, and we had the point 2, 4. And I had those on my table, so I'm going to label these. I want that to be skinnier. So this was negative 2, 4. I'm going to call that A. This is negative 1, 2.5. I'm going to call that B. This was 0, 2. We'll call that C. This is 1, 2.5. We'll call that D. And this was 2, 4. We'll call that E. So we're going to come in now and we're going to flip those points around. So we're going to go to the point 4. So I'm going to have to come over. And we're going to go to negative 2. That's our A. And then 2.5, negative 1. That's our B. Right? For 0, 2, we go to 2, 0. That's our C. We go to 2.5, 1. That's our D. And then we have 4, 2. So this was 4. So we come 4, 2. That's our E. So when I connect these in A, B, C, D order, I end up with a sideways parabola. So my function, let's go in here. Let's join these points with a smooth curve, getting our happy parabola. Right. So is our inverse, right, is this a function? Well, yes, right? Why? Well, we already know by its equation it's a quadratic function, but it passes the vertical line test, right? Any vertical line that I draw is going to intersect my quadratic once and only once. When we plotted the graph of its inverse, right, was this a function or relation? Well, if we try to draw a vertical line here, it crosses that axis at 2 separate points. Right? So, is the inverse a function? Answer, right? Right. Is this a function or relation? Answer, it is a relation. It doesn't pass, right, the vertical line test, and that would be the inverse doesn't pass. Okay. We will also notice that if we come in here to our function and draw a horizontal line, the function crosses the horizontal line crosses that function twice. It does not pass, right? The function itself does not pass the horizontal line test. All right. So we want to find the equation for the inverse of this quadratic. So we have our equation. First thing we do is replace f of x with y. So we have y equals 0.5 x squared plus 2. Right? This is our function. Now we're going to find our inverse. By replacing y with x and replacing x with y. And we're going to solve this equation for y. So I'm going to subtract 2, and I get x minus 2 equals 0.5 y squared. Okay, I want to get rid of the 0.5, that's 1/2. So if I multiply both sides by 2, I'm going to get 2x minus 4 equals, right, 2 times 0.5 is 1, so I get y squared. And then to get rid of the squared, I'm going to take the square root of both sides. But when I do that, I have to put plus or minus outside the left side. So I end up with y equals plus or minus the square root of 2x minus 4. Right? So, question, is there only one expression for y? The answer is no. There are 2. Right? This says that y is equal to the positive square root of 2x minus 4, right? But it also says that y could equal the negative of the square root of 2x minus 4. That is 2 separate expressions, definitions for y. So, is the inverse of f of x a function? No, right? There are 2 y's for each x. If I were to put in 3 for x, right? If I were to make that a 3, I would get 2 times 3 is 6 minus 4 is 2. This would give me a positive square root of 2. If I were to put in 3 for this x, I get 2 times 3 is 6 minus 4 is 2, but y would give me the negative square root of 2. So, why can't we redefine y using this notation? Because y is not a function. Now note, if we're going to graph this on a calculator, we can graph our original function by entering it at y1 into our equation editor, our function editor. But if I want to graph, let's not write it this way, if I want to graph the inverse, I would actually have to enter 2 equations. Right? For y2, I would do the positive square root, which would give me the top half of this parabola, and then I would have to enter the negative square root, which would give me the negative part of that parabola. Right? That would be that one. If I wanted to plot the axis of symmetry, that is always y equals x, and so that would come in like that. If a function is 1 to 1, it is called invertible, which means it's able to be inverted, and its inverse is a function. Okay, this last one is a you-do problem. But I'll just walk through that. No, I'm not. I'm going to leave that as a you-do. You've got all your notes up ahead. And I think it's time that we stop this video. So work on this. You can do it. I believe in you.